What up? What up? Let me try something with this here microphone. Okay. How's that? Cool. Let me try one more thing. One more. All right. Very well. Okay. So we are starting with Clojure. Let me also ping the Discord. Okay. We're taking a look at Clojure. Here on Answer Everywhere, we'll look at its source code. It runs on the JVM, but is it written in Java or is it written in Clojure? We'll find out. Hollywood stars. Okay, so 57.6% Java, 41.9% Clojure. So mostly Java. That's not the least bit surprising. You might expect it to be more self-hosting, but hey, what do you know? So I've never used Clojure. Have you used Clojure? Have you ever gotten Clojure? So I assume this is named after the Clojure programming thing. Programming doohickey. Abstraction. In programming languages, a closure, also lexical closure or function closure, is a technique for implementing lexically scoped name binding in a language with first-class functions. Operationally, a closure is a record storing a function, together with an environment. So the environment is essentially the environment in which the function is to be evaluated. Environment is a mapping associating each free variable of the function to variables that are used locally, but defined in an enclosing scope, with the value or reference to which the name was bound when the closure was created. Unlike a plain function, a closure allows the function to access those captured variables through the closure's copies of their values or references, even when the function is invoked outside their scope. All right, good stuff. So let's look at how it's implemented. We are near the end of the old regime where I took a bunch of requests and I'm plowing through that backlog. We're going to do 30 minutes time boxed for each of the repos today. And then after the backlog is done, we will enter the new regime in which the focus will be, I'll still take requests. We'll firm up how the requests happen so that there's less to rate limit things and have more of a curated approach where a significant part of the curation is done by the community. And then that will be balanced with building things, including building up the Holy Hedge Fund and the Cult of Pythagoras and the code that I've been working on. All right, so Let's set a timer. And let's look into Clojure. I'm on the GitHub repo. I think this is the real live place where this lives. And what? Okay, so we have code gen. Code gen might be important. I don't know how much code gen they do. We also have tests. I'm kind of feeling like looking at tests, and then we have doc, whatever pprint is. This is, I'm going to guess this documentation is mostly like code-based documentation, and maybe that's not my thing. And in source, we have assembly, clj/Clojure, jvm/Clojure, resources/Clojure, and script. I'm guessing resources is like static assets. So, and I will assume, based on Java's naming convention, that jvm/Clojure is the Java implementation. clj/Clojure is the, I guess, once we've bootstrapped on the JVM or however we're doing it, that should be the stuff in here. And then we have assembly, which might be just super optimized routines. And let me just verify, but I believe Clojure is a Lisp. Let's get the basics right. It's a Lisp programming language, a functional dialect. I don't know what a non-functional dialect of Lisp is, but okay, so that's source. And then in test, we have Clojure and Java. What's more important? Clojure, test, compilation, reflector. So there's some amount of reflection, test, dispatch. There's not a lot of Java tests, at least in there. A few in the Clojure/test. Let's see what's in Clojure. Test, Clojure, and helper. Cloj. We have many more tests in Clojure, which makes sense, including gen class, annotations, compilation, Java, pprint. Preprint must be pretty print, right? Protocols. Examples, hash collisions, more examples. Should we look at examples? I guess the file name is Kulj. This is definitely Lisp. So the way Lisp works is the head of the list is the, it's like the function. I don't know I forget what the terms are, but the head of the list is the function, and then everything after it is data. And it's just, it's like an S expression. If we're reading Lisp, let's make sure that we have just a general understanding of, oh, this is the speech thingamajig. It's essentially the lambda calculus, right? Okay. Trying to see if we can get a good description of. We have control structures, evaluation, and the read eval print loop. Lisp languages are okay. Maybe that's not the entry point I thought it was. List structure of programming code. Exploitation by macros and compilers. A fundamental distinction between Lisp and other languages is that in Lisp, the textual representation of a program is simply a human-readable description of the same internal data structures, linked lists, symbols, number, characters, etc., as would be used by the underlying Lisp system. Lisp uses this to implement a very powerful macro system. Like other macro languages, such as the one defined by the C preprocessor, for the C, Objective-C, and C++ programming languages, a macro returns code that can then be compiled. However, unlike C preprocessor macros, the macros are Lisp functions, and so can exploit the full power of Lisp. Okay, so we've looked at Emacs Lisp before. These are just tests. That's not so interesting. So let's go into how this is defined. So in the Java folder, we have ASM, which I assume is assembly, the Java API. I don't know what that is, lang, and main. I'm going to guess lang is the place to be. We'll look at these other folders as well. And we will open up this Clojure directory too. And this is where most of the, at least we have more files. We saw that there's more actual Java code written. That could be a reflection of the fact that Java is more verbose, rather than a reflection of the fact that it's mostly Java. And in core, we have some stuff. We'll open core, we'll open Java. I refuse to open preprint. REPL might be interesting. We'll open core.Kulj. I don't know what instant is. Maybe we'll look at instant. Maybe we'll look at main and math. And parallel might be mildly interesting. String, is that interesting? I'm not sure. Stack trace could be amusing. Walk, I'm going to guess is walking not only lists, but traversing other kind of data structures. And we have zip. And what's an assembly? Assembly, I guess, is like assembling maybe the packaging. I'm being told that YouTube is not getting enough data. Let me see if I can back down this stream latency or anything. No, I don't know. I don't think I'm streaming at like higher than normal. I think it'll be fine. I'm going to repost the videos anyway. Okay, slim. So this is just some XML. This is not an assembly language, I guess. What did I just look at? Distribution or slim? That's slim. And then distribution, I guess this is describing like parts of the source code, I guess, to distribute. So we can safely ignore that. That's good. Now we have to choose in our remaining time, which is about 23 minutes, to split between Clojure and JVM. I have a feeling if we start looking at Clojure, we will look at it forever. And we will forget. It's kind of hard when you're in one programming language, it's kind of hard to see the boundary to the language it's implemented in often. It's easier to see where the implementing language calls the newer language. So for that reason, maybe we'll just at least take a look at what's in the Java folders. I is probably interface, assuming they're just using this naming convention. We have a bunch of interfaces like proxy, record, reduce, persistent stack, persistent map, lookup, some indexed stuff. I don't know what indexing what. Don't know. Map stuff, murmur. I don't know what murmur 3 is. RT, possibly real time. Record iterator, ref.java, seek enumeration, set table, tuple. So these look like a lot of data structures. Function, I guess we probably should look at counted cycle. Maybe we'll look at cycle, compile and compiler, chunked cons. So cons is the Lisp operation that that adds a new element to the list. Do we have a cdr? We don't have a cdr. So we'll open a few of these. In the API, we have just clojure.java. That might be an interesting entry point. And here's clojure/asm. We have things like okay, this looks like frame. I'm going to guess this may be a stack frame, a method writer, a method visitor. I guess we'll look at method writer, method visitor. Well, I guess we'll look at handler, a type path, and a type reference and a type. I'm going to guess a path is like possibly like a fully qualified name. There's some annotation stuff, byte vector. Do we care about byte vector? Probably not. Commons. I don't know if this is generator, method, table switch generator. I don't know if these are interesting. I guess we'll open up method just for funsies. All right, and so now we're in code. Cool. And let's just prepare the other window. Should we? No, let's not, because I'll get confused about which window is which. Wonder if there's a quick and easy way to like highlight, to change the coloring of these windows so I can know, so I can like, color them. Okay, so here's function.java. There's nothing. It's a public interface. It has no constraints. Cycle.java. Actually, let's start with, I thought clojure.java was down here somewhere. Here, let's start with clojure.java. We get this comment, the copyright comment. This is the package java.api. And we're importing a few things, mainly the function interface, what is a symbol, what's a variable, RT, I'm guessing, I guessed before was real time, but it's probably runtime, right? When they say runtime. And then what else do we have? Okay. The Clojure class provides a minimal interface to bootstrap Clojure access from other JVM languages. To bootstrap, the Clojure class provides a minimal interface to bootstrap Clojure access from other JVM languages. So this is not really fundamental to Clojure. This is going to be kind of like a foreign function interface, but restricted to the JVM. Maybe it is interesting. Maybe will tell us a little bit about Clojure. We'll take a quick look at the ability to use Clojure's namespaces to locate an arbitrary blah, blah, blah. A convenience method for reading data using Clojure's EDN reader. I don't know what EDN is, but that's actually not so interesting. This is kind of like just string manipulation, I guess, because the JVM is operating on strings fundamentally, in some sense. So here's Clojure ASM frame. Let's see what kind of frame it is. The input and output stack map frames of a basic block. Stack map frames are computed in 2 steps. During the visit of each instruction in method writer, the state of the frame at the end of the current basic block is updated by simulating the action of the instruction on the previous state of this so-called output frame. I don't know how you're going to simulate that. The state of the frame at the end of the current basic block is updated. After all instructions have been visited, a fixed point algorithm is used in method writer to compute the input frame of each basic block, i.e. the stack map frame at the beginning of the basic block. See method writer. Output stack map frames are computed relatively to the input frame of the basic block, which is not yet known when output frames are computed. It is therefore necessary to be able to represent abstract types, such as the type at position X in the input frame locals, or the type at position X from the top of the input frame stack, or even the type at position X in the input frame with Y more or less array dimensions. This explains the rather complicated type format used in this class explained below. Okay, so this is looking complicated, possibly important, but I think it's going to be difficult to follow this without knowing more about Clojure. So maybe I'll pop that off in its own thing. I doubt we will get to it, but that looks a little bit too technical for where I am, at least in my understanding of what's going on in the code. Let's see what else we have. This is the Clojure window. Let's go back to Java. Is this Java? Okay, so here's method writer. ASM, a very small and fast Java bytecode manipulation framework. Okay, so this is called it ASM. It's really manipulating bytecode, it looks like. So method writer extends method visitor. A method writer is a method visitor that generates a corresponding method info structure as defined in the Java virtual machine specification. So the JVM specification says that you have to have some sort of method info structure, and this is going to comply with that, just allowing it to run on the JVM, maybe allowing other things to contact it. But that's not something that I really care about. Method visitor, I'm going to guess ASM is all part of the same project, so I'm going to ignore that for now. Chunked cons, is it interesting? I'm not sure. Chunked cons takes an iPersistent map, which is called meta, maybe metadata, and a chunk, which is a thing that implements the chunk interface, and more, which is a sec, maybe some kind of sequence or iterator. We're going to call this super, we're in Java, right? So we're going to call super on the meta thing to call its, what's it called? Initialization function, whatever that's called in Java. And then we're just keeping track of the chunk and the more. And chunked cons is a function that takes in a chunk and some more and calls this. And that just, I guess, produces the chunked cons object. When you call first, we ask for the nth, I guess, element of the list, which is just, and we're asking at n equals 0, so that's the head of the list. Next is going to call, if we have more than one chunk, then we're going to return a new chunked cons, dropping the first. So It's essentially that's like tail. And we're going to call more on that. That's just consuming the first element and getting the what's left. And we're going to return chunked next. And what is, I say chunked first just returns chunk. This is like the head of the list. Chunked next returns chunked more dot seek. And presumably seek is like the iterator, the thing that makes it iterate. And what's chunked more? Chunked more returns an iSeek. And if more is null, if underscore more is null, I guess we're at the end and we have the empty list, I think is maybe what that means. And then otherwise we return the list. So that seems to be an implementation of a list. I don't know what makes it chunked. I guess I didn't really get a chunky feeling from it. We have iChunk. Should we find out what iChunk is? iChunk sounds like it's a novel about a person's struggle with weight loss. So iChunk has us drop first and reduce. I don't know why it's called chunk. Seems like pretty regular listy, but maybe it is chunked in some important way. Here's compiler.java. We have a bunch of symbols. Like these are the symbols in the language of Clojure rather than Java. These are things like def, loop, recur, if, let. These will go at the head of our list. So if we see some, let's go back to the Clojure article. Def should define a function. Oh no, defin defines a function. What does def do? I don't know. Do we have a defin? We have emit for defin. I'm not sure. How about we look up Clojure loop? So loop does seem to be a reserved word, but it's not all caps. So I don't know. Maybe this is the Java side of stuff that's implemented in Clojure, but we'll see. So we have def, loop, recur. I'm going to guess is a recursion or a recurrence. If case, this is conditional control. Let fn. These should be binding a name to a variable. Do, I'm guessing is a do loop. Quote is quoting treat the following as like a string rather than interpret it. The var, I don't know what the var is, import dot assign def type, etc. We also have try, throw. This is like error handling. Monitor I'm going to assume is the mutual exclusion monitor. And we also have catch and finally. We have also max position arity is 20. I don't know if that means you can only have a 20 arity function. We have things like object type, keyword type, etc. And here's some stuff about local binding. We have this var local end is equal to var.create null set dynamic. It's some dynamic variable, I guess, probably set to null initially. It can be anything. Loop locals, we're calling create. We're not passing null to it, but it's a set dynamic. Maybe this is for dynamic typing. Keywords, vars, etc. We have things like source. Source is a var intern with a namespace. Clojure.core, etc. Yeah, so this is source code stuff. This is interesting, but we're going to kind of breeze through it. Here's tail call. This will, I guess, check if we're in a tail call. It returns a Boolean, and you pass it in a context. And if the context is c.return, so I guess we're returning, and the method return context, when we dereference it, it's non-null. And if we are in catch finally, if we are not, I guess, in catch finally is probably what this means, then we return true. So we return true if we're not in in a catch finally block, and we're returning, and the method return context is non-null. You have a class def_expr, def expression, which extends expression, and it's got things like a var, presumably for holding variables, an init expression, a meta expression, whether init is provided, whether it's dynamic, a source. I guess we're going to keep track of the source in the line and the column. We have this bind root method, void bind root object. This looks like maybe this is essentially generated Java code. This is some definition that we're going to use to generate a Java class somehow. And we'll move along from here, but this is actually interesting, the compiler.java. Maybe we'll come back to it if we have more time, which I don't think we will. Here's compile.java. And maybe this is the thing that just kicks off the compiler. We've got a main function, so it's doing some execution. I'm going to guess we're importing compiler. No, we're not. But what functionality do we have? We just have really main. So maybe this is like a thing that you can run on the command line. Var push thread bindings. I think probably runtime map compile path. So this is the thing that you invoked, I guess, to do the compiling. I don't know why it doesn't import compiler. I guess it doesn't really matter. Maybe runtime has a reference to compiler. And here's cycle. Cycle is probably not so important. This is probably cycle detecting, but if there's a runtime.java, we should look at that. rt.java. We don't have a class level description, but we have Boolean t is defined to be Boolean true, and f is defined to be Boolean false out. And we've got these intern symbols. I'm not sure if this is interning it means it's an internal symbol. We have things like Boolean, byte, compiler, double. These are common types. Big decimal, runtime exception, security exception, etc. Read, true, false, unknown. And what? It's just a bunch of stuff. So this is definitely the runtime, and it's big. 2,400 lines of code. And we're not going to really be able to make much sense of it. So let's move on to the Clojure code. I'm going to ignore frame. So where do we want to be in Clojure? Let's see. How about core protocol? We don't want protocols reducers. We have about 7 minutes left. Process shell IO. I think those are not going to be fundamental. Reflection, I think, is not going to be essential. So REPL just has deps.clj. Clojure REPL deps provides facilities for dynamically modifying the available libraries in the runtime when running the REPL without restarting. Dynamically modifying the available libraries. So this is, so you don't have to restart when you change things. Here's core.clj. This looks like a command line parsing thingamajig. Maybe we're defining some stuff. Maybe this is just notation. Args list. This is like documentation for the function. This function creates a new list containing the items. And added. Maybe this is the version of Clojure. It was added. So what's the function name? List maybe. Okay, so list. And then whatever this is, .clojure lang persistent list creator. So I'm guessing that this line is telling you the Java method. That's being called. So creator is an I function. So I'm not sure. I guess, does that mean it's not a method? Something. Here's the definition of cons. Returns a new seek. Oh, I guess seek. This is a sequence. I thought it was some sort of iterator, but maybe it's, I don't know. Let's look up Clojure seek. Or let's just look for seek in here. Maybe seek.java. Aseek, iSeek. And iSeek is a persistent collection, a persistent functional sequence interface. iSeeks are immutable variables, i.e. neither first nor rest changes or invalidates the iSeek. Okay, so it has essentially the same. You can get the first, you can get the next, you can get more. More, I'm going to guess, is essentially tail. Next should be the next element, and cons is like adding a thing. So it's kind of like an iterator, except we can manipulate it and we get a new thing back. So it's maybe more like a list, a classic list. So cons is the classic cons. We've got this function star thing. I don't know what that notation means, and I don't know what this pointy nose smiley face is, but we see static cons brackets x seek, and then Clojure line RT. I guess this is some call to the runtime. We're going to call cons x seek. X seek is the arguments list. So this is, I guess, a list of arguments. And this, whatever this thing is doing, this is essentially allowing us to mix in Java, I think is what's going on here. Unless this is a thing that's like reified into Clojure from the Java code in some other in some other library. But, and I don't know what fn star means, as opposed to fn and like dot. Let's ask the AIs. Well, let's ChatGPT. So the following is Clojure code. Why do some entries begin with dot and others with fn star? And how is fn star different from fn? And what does mean the pointy space smiley guy? Entries starting with a dot are likely symbols that refer to existing functions or variables in your current namespace. Okay. Function star is an anonymous function definition with a twist. So it's essentially a lambda. It's similar to function, but with potential performance optimization. Like fn, it creates an unnamed function on the fly. However, fn star might be inlined by the Clojure compiler. Okay, so it might be inlined. Fn is a standard way to define an anonymous function. And this smiley face thing is meta tag is used to attach metadata to Clojure forms. And I guess forms include functions, variables, data structures. And its metadata is additional information. So it's attaching metadata. And what is the metadata? Maybe the arguments. The syntax for attaching metadata is pointy nose key value. For example, pointy nose doc, this function, blah, blah, blah. In your code, you might see other meta tags, but it's okay. So this is what? So doc, this defines a doc, and this defines a static cons. I guess, is that metadata? Why? I don't know. And then here's more. These seem like the main definitions of the like classic Lispy functions. We have sec question mark vector map, a map question mark. I don't know if map has a question mark because it's nullable. Return true, or maybe because it's a Boolean. Return true if X implements I persistent map. And so we're going to have this fn. It's not going to be inlined, I guess. And so the static map question mark and taking X as an argument. And we're going to call instance question mark of Clojure lang I persistent map. So this thing in here, I guess this is Clojure and not Java. So that's probably what was going on up here. Although we should have the ability to call Java methods pretty seamlessly. I've never really used the only JVM languages I've used are Kotlin and Java. I haven't used any of the functional stuff, but now I'm curious, like, what are we importing? We should be able to import the stuff from Java, but it doesn't seem like we're really importing anything. We have this def macro import. EDN you can think of as Clojure's JSON, but better. In particular, extensible. The loop construct is a usual. Yeah? Okay. So the loop is just looping, and the .fn arg syntax is for field member access, but in prefix form. Okay. So the dot is the field accessor dot, like in Java. Thank you, Elsie. That's extremely helpful. So here, I guess we're calling the creator field of the persistent list. Is that the idea? Let's see if there's a persistent. Well, no, that's not going to work. See if we can find dot creator. I don't know. And then that's for metadata. Yeah. So such as provenance, or as seen here, used in compilation generations. Okay, cool. Thank you, Elsie. That's extremely helpful. All right, here's instant.clj. I don't know what this is. Clojure instant. So this is some namespace annotation. We're going to set warn on reflection, and we have some convenience macros that, like, this private thing will fail. Throw some sort of, oh no, this is, I guess, maybe just the annotation is that it's private, and Elsie is saying that the some of the times the annotations are used for compilation and generation. So I'm guessing this is to annotate that it's a private message or something along those lines. Yeah, okay. So we have this parse timestamp thing. Maybe instant is like for time stuff. Return a function which constructs an instant by calling constructor after first validating that those arguments are in range and otherwise plausible. So this is calendar timing stuff. I guess instant is maybe a little bit like now. Here's main.clj, top level main function for Clojure, REPL, and scripts. So this is, I guess, mainly for REPL, which I guess what else would the top level do? We have demunge. Given the string representation of a function class, as in stack trace element returns a readable version. We can root calls, returns the initial calls of an exception or error by peeling off all of its wrappers. That's useful. This should just be basically be a tree walking exercise in Lisp. That's probably a fun thing to look at, but we are going to plow along. We're actually out of time, but let's see if we can see a little bit more. We have with bindings executes a body in the context of a thread local bindings for several vars that often need to be set, like var non-reflection, math context, etc. Seek is the almighty abstraction. Okay. Yeah. Thank you. All right. File name x triage. I don't know what x triage returns an analysis of the phase error calls. Okay, so there's a lot of error handling stuff, which I think makes sense for a REPL. And here's this is the definition of the REPL, I believe. Generic, reusable, read eval, print loop by default reads from in, I'm guessing standard in, and writes, or maybe Java in, and writes to out, and prints exception summaries to error. If you use the default read hook, in must either be an instance of line numbering pushback reader, or duplicate its behavior. Blah, 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 blah. Init is a function of no arguments, initializing hook called with bindings. Need prompt, a function of no arguments called before each read eval print except the first. The user will be prompted if it returns true. For example, if we are in and at line starting in and identity is true, then I guess then we will need a prompt. So we have some options. I don't know if these are the arguments to the function. We are defining some stuff here. Cul might be class. Let cul get context loader thread current thread. I guess this seems to be getting context from the current thread. And then we're going to, I guess, call the set context loader to something, whatever dynamic context class loader of CL or something along those lines. Here's some more let bindings, I assume. And these are some, I guess these are it's defining some sort of keys. Perhaps this is a kind of map, I don't know, but init need prompt flush read eval print caught. Or, and then I don't know what keys or means, but we have init need prompt flush read. Read is corresponding to REPL read. Need prompt. This seems to be the like the default definitions of these functions. I guess this is like an empty. There's no initialization hook. This is, I think we recognize this as the what it told us was the default implementation of need prompt. I'm guessing REPL prompt is the default implementation of prompt. Flush with flush. Read is implemented as REPL read. I think that's what's going on there. Then we'll call apply on the hash map options. Or rather, we'll apply, I guess, the function hash map to options. And then do some prompting stuff. And then read eval print. I don't know what's going on here. I don't know where this scope is. Are we still in, have we terminated this bracket? I don't know. I don't think so. This is the problem with Lisp. You have to figure out where all the parentheses end. But this, I'm going to guess, is aligned so that when we do terminate the bracket, it'll be like down here. Or not. Maybe it's here. At any rate, I don't know syntactically what this is. Maybe this is defining the function read eval print to be a function of no arguments. It's going to try some stuff. What is it going to try? It's going to try to, I assume this is let binding. Let bind read eval as whatever star read eval star is. And I guess this is probably trying to get the input. Try read with known, read request prompt, request exit, and maybe throw an error if there's a reader error. Or request prompt, request exit. I don't know what set 3.2, set 2.1, set 1 value is. And then some erroring out, and we might have an exception. And then we have some with binding stuff. So I don't really know enough about Lisp to know what's going on there, but that's some implementation of a read eval print loop. Timestamp like data is instant. Thank you, LC. And the ... are vectors, i.e. arrays, as opposed to, and have a specialized notation. Function argument. Okay, so the function arguments are provided as vectors. That's interesting. The one I'm looking at are the bindings in the let. In that case, it's assigning a function to the name. Yes. Okay, cool. I think that's, there's a little bit of a delay, but I think you were saying that here, that this read eval print is being assigned this thing. I don't know what keys or is, but this must be like a dictionary like notation. Not Lisp. Let's look up Clojure. The keys key can be used to further remove duplication. The as and or keywords can be combined into a single destructuring. So it's something about destructuring. Associative destructuring. And then we also have sequential destructuring. Associative destructuring is similar to sequential destructuring, but applied instead to associative key value structures, including maps, records, vectors, etc. The associative bindings are concerned with concisely extracting values of the key map by type. And so what does OR do? Also allows you to supply, so OR allows you to supply a default value. I don't know why that's not called something more informative than OR. The value for colon OR is a map, where the bound symbol here, category, is bound to the expression category not found. When category is not found in client, it is instead found in the colon OR map and bound to that value instead. So here's the example. Here's where it says OR category not found. And I guess this is where it tries to bind to the original category, perhaps. Something like that. Keys is merely a name using, okay, cool. That's the, thank you, Elsie. And we're out of time. Let's see if there's anything else we want to see here. Math. Math is always cool. Let's look at sign. Sign returns the sign of an angle. I guess we're just calling math sign maybe in Java. I don't know what math / sign is. So I think we're just calling out to a Java function. That's the nice thing about implementing something on the JVM is you get to call the Java functions. So there should be a sign implementation here. Yeah, okay. Parallel, deprecated wrapper of the fork join library. Okay, so this is deprecated and it's using an underlying Java library, I think. Stack trace is interesting. I think the intuition behind stack traces in something like Clojure or Lisp is that because the structure of the program is the same as the structure of the code, you get a lot of, it's easy for scripts and other utilities to understand the structure of the code and to present it back to you in a way that it's clear to you because you wrote the program in the same syntax. So people who work in Lisps, I think, often describe one of the advantages of the being able to debug things and modify things on the fly because of this structural similarities. By similarity, I mean identity. Walk.clj, I guess this was probably some sort of traversal, a generic tree walker with replacement. So I guess we're walking trees in particular. Traverses form an arbitrary data structure. Inner and outer are functions. Okay, so this is going to do some data structure traversal. Zip should be functional zip. A functional hierarchical zipper with navigation, editing, and enumeration. See Hewitt. And definition zipper creates a new zipper structure. We have branch is a function that given a node returns true if we can have children, even if it currently doesn't. Children is a function that given a branch node returns a seek of all its children. Okay, so what was the implementation? Okay, so branch, children, make node, and root. And then we've got this annotation thing. Zip branch is set to branch. I guess we're maybe annotating with the arguments that were passed in. And then what? And then passing and also root nil. So this is like the maybe the initial case of a recursion. I don't. So these are all arguments. I think these are annotations, if I'm understanding correctly, and these are some new kind of arguments that we're calling. Maybe we're just returning this vector or something. Vector zip, XML zip. A node is just like, I guess, a location in the code. We have this children function, which you call on a location, and if branch question mark of the location, then So if should be if the true case and then the false case. So the false case, we throw an exception, it looks like. And in the true case, we call zip slash children. I guess slash is used here to a kind of namespacing thing. So like zip is the like class or module that we're in, and children is maybe the function on the we'll call meta on the lock. I guess getting the metadata, and call node on the lock, or create a node out of the lock, perhaps. And that's going to call the zip children function. I don't know how that's different from the function we just looked at, but returns a seek of the children. So this should be some sort of recursive thing. So if we're branching, we should be calling, I guess, zip on both branches. This colon thing, I'm not sure whether we've talked about yet, but I think this is essentially somehow calling zip on both branches somehow. Yeah. Okay. No, I haven't even noticed the typos. So I'm looking at what LC is saying. That is merely a literal textual. Yep. So of the data structures, for example, lists representing the program, you can think of the program as a list or as an express program. As such, you process them exactly as you would with any other instances of such data structure. Yeah, for sure. So we've looked at a couple of Lisps. No, we've looked at a couple of functional languages. We've looked at some Haskell. And so things like zip will be familiar from Haskell. We've looked at Emacs Lisp, which I also don't write Emacs Lisp. I don't write all of the Lisps. So I know just enough Lisp to get by, but I wouldn't be able to like write a program in them. And at some point I should, but I am a big fan of some of the listy functional languages like R and Haskell. And I'm sure Lisp is really cool. I'll just give you my take. My take is that Lisp is, I believe, essentially an implementation of the untyped lambda calculus. I really like types, and so Haskell is like a typier version of Lisp in a sense. And one of the nice things you can do in Lisp that you can't do in Haskell is because of the untyped nature, you get it's a lot more of a dynamic language like Python, whereas Haskell has more of a rigid structure. And just as a personal preference, I like having the rigid structure to prevent you from doing things. So to make sure that what you're doing is something you always understand. Whereas I find in dynamic languages, there can be kind of like bugs that are harder to track down because of the flexibility. So you probably, once you get really good at it, that's less of an issue. But I'm not sure, for example, like if there are any really huge Lisp databases out there. But surely there are somewhere. Okay, so that's Clojure. That's Clojure for now. We may at some point return to other Lispy stuff. We may at some point return to Clojure, but we'll leave it there for now. So what are we looking on next? OpenFoam and V8. You know what? I'm going to go with. I have a feeling OpenFoam is going to be more cognitively demanding, and I'm going to put that after V8. Like, I mean, OpenFoam is going to be a lot of me not knowing what's going on, which Lisp just was. So I think V8 might be a nicer break. So LC is saying just enough Lisp to get by is actually valid for, what is this word? For both the extreme language of, yeah, cool. All right. V8. How about just V8? We're taking a look at V8, the JavaScript engine that runs Chrome and Chromium and Microsoft Edge and everything else that's built on Chrome. And probably, I think, also Node. This is a big and intensely technical project, and we're only devoting half an hour to it. So we're just going to scratch the surface. We're going to give the surface a teensy tiny little scratch on its nose. And that's that. I'm going to look at the GitHub mirror. The official code repo is in what I assume is Garrett. It's some Git tiles thing. And I do like Garrett, but I don't really like Git tiles as an explory thing. Yeah, this looks totally like Garrett. Okay. All right. And Node. Yep. Cool. Okay. So this is the V8 JavaScript engine. What's going on here is that my understanding, I wasn't there, is that the idea was to make the browser usable as a way to deliver apps so that Google could compete, for example, with Microsoft and do things like have a usable web client, namely Gmail in the browser, have a usable document and spreadsheet editor, and so on. And so that was the original idea of Chrome. And to get that working, they optimized the hell out of JavaScript. And I'm sure they hired amazing people, both researchers and people who had built other important VMs in the past. And they made it happen. And now everything's on the web. But I'm going to assume that this repo is probably pretty intense. So third party is Google's way of this is where other people might put these in lib. These are like third party libraries that they depend on. GNI, I'm not sure I remember what that is. Custom deps, I feel like I've seen it, but I forget. Bazel has its own directory. I'm not sure why. Maybe this is just like Bazel-y stuff that they needed at the time. And here's the source. I'm going to guess most stuff is in source. We have also infra, which is maybe not important. Include has CPP GC, I'm guessing garbage collection, lib platform, some V8 data stuff, V8 inspector, V8 profiler. These might be just like tooling, and also samples. Should we look at Hello World? GNI, what is GNI? Oh, this is not related to the samples. So GNI has the v8.gni. GNI file format, Google something. The GN language. Introduction. It's an extensive built-in help system which provides reference for every function and built-in variable. Okay, so this is some, I guess, help stuff. And we don't need it. Let's see if we can find a V8 architecture diagram. I'm just going to open these willy-nilly and see if we can determine anything interesting from them. So we initialize the environment, we compile, we generate bytecodes, we interpret the bytecodes and execute, and there's some optimization. So this just looks like just-in-time compilation. There might be de-optimization. That's not so informative, but so we have some JavaScript source code. It goes into a parser. There's an abstract syntax tree. This is all stuff we've seen before in other compiler type stuff. We have interpreter ignition. And then I don't know what ignition means, but it's going to generate some bytecode. We've got a compiler turbofan, which makes optimized machine code. And I guess maybe that mixes with bytecode. This is a YouTube thumbnail because it's called Max Res Default. And environment browser, Node.js, V8 engine. Okay. So these diagrams are just telling us that it's doing compilation. This is unrelated, but looks like maybe some machine learning stuff. Cool. This might be interesting. I don't know what turbofan is, call stack execution context, heap memory allocation, Orinoco garbage collector, ignition, JS library, liftoff assembly. Let's look up these things. Liftoff assembly, Orinoco garbage collector, perhaps named after the song Orinoco Flow. So here's the Orinoco thing. There's some presentation. The garbage collector has a few essential tasks to identify. Okay, so is there anything interesting that's going on here? I'm not sure. Maybe we'll just keep these up in the background. Liftoff assembly. I don't know if this is finding anything. And what was the other one that I wanted to see? Turbofan. Well, turbofan V8, and how about liftoff V8? I think this is going to save us time in the long run because we'll probably see some of these code names in the code, knowing Google. So it would be nice to know what they are. In 2018, V8 6.9, nice, includes Liftoff, a new baseline compiler for WebAssembly. Liftoff is now enabled by default on desktop systems. Since WebAssembly launched more than a year ago, adoption of the web has been steadily increasing. Adoption on the web. So something about WebAssembly and benchmarking. What is turbofan? It's one of V8's optimizing compilers, leveraging a concept called Sea of Nodes. I will read Sea of Nodes, and I will read the high-level overview of turbofan. And I won't look in, I'll read them later. Okay, so now with that, let's dig in. I'm not sure what we really want to see. Let's see Hello World. We've seen, I think we looked at Node. We saw somebody calling the V8 code. We are including this lib platform stuff. Isolate, I think, is a term. I think it's isolate as opposed to isolate. We initialize the ICUDEF default location. I don't know what ICU is. Initialize external startup data, new default platform, initialize platform, and initialize. This is just kind of boilerplate initialization. I'm not sure what all that does, but I think that probably some of it makes it so that you can have different versions of V8 running on the same machine, and they don't interfere with each other. Create a new isolate and make it the current one. And maybe also isolates are used to isolate tabs or something, so or different sites. So we create params and an array buffer allocator. It's some allocator, I guess, for allocating memory, and we're calling isolate new on create params. Did we do anything with create params? I think these are just the default ones, perhaps. Or then we have some block here. I don't know what this block is part of. I don't see like a function call, but maybe I'm missing something. We call isolate scope. So I guess we're setting the isolate scope to the isolate we created. We're creating a stack allocated handle scope. So we're creating a handle scope for the isolate. And these look like just function definitions or something. And then we're going to enter the context, and then create a new string containing the JavaScript source location. So isolate hello world, compile the source code calling v8 script compile, to local checked. I don't know what to local checked. Maybe local means it's running locally, and checked maybe means type checked or something along those lines. And run the script to get the result. So in C++, we can just run the script, to local checked, and get the result, which is a v8 value. I guess we have to figure out what kind of value it is if we want to use the result in C++. And we convert the result to a UTF-8 string and print it. How do we know it's a UTF-8 string? I'm not sure. I guess we can convert anything to a string because it's JavaScript, right? What's it going to do? JavaScript is basically all strings all the time. And so on. Okay, so what is interesting to me here, I think we should probably take a look at compile, v8 script compile. So the script is the model for JavaScript. Script run is going to execute the JavaScript. There's this isolate stuff, which is probably important for like embedding JavaScript into your application. I think I remember seeing stuff about embeddings before. Not machine learning embeddings, but some other kind of embedding. All right, let's see compile. We have API, assembly, JS, base, baseline, bigint, code gen. I'll open code gen. So compiler we'll look at. We have the deoptimizer. I'm mostly interested in when we would want to deoptimize. Let's ask Gemini. So when does the V8 JavaScript engine deoptimize? And we'll come back to that in a second. Fusilli, I guess is a pun on the fusilli pasta and fuzzing. Handles, heap, IC. I don't know what IC is. Interpreter. We look at interpreter, lib sampler, maglev. Maglev within the context of Google is a load balancing thing. I'm not sure what's up with it here. Regular expression, profiler, roots, runtime. I guess we'll look at we'll open runtime and sandbox. We may not actually look at it. Tasks, temporal, third party, torque. I don't know what torque is. WebAssembly. I guess we'll open WebAssembly. But did we see script? I didn't see script. Let's go back here and see if we're if there's anything. We have include. Please tell me there's not a separate include directory. Here's V8 script, the header. Maybe you do need to have a separate include directory in some cases. I don't really know the details. We'll look at a couple of these headers. V8 value, I guess we should look at. Let's go over here. And v8.h. That might be too intense. How many lines? 88 lines? Okay. Not bad. So we're including all the things, all the headers that you can ever imagine. And then in the namespace v8, we have a platform class and shell.cc, a simple shell that takes a list of expressions on the command line and executes them. Okay, so I could download this and run Bazel on it, but I mean, that's interesting. I guess you can just execute JavaScript from V8 if you have the source code, and maybe you can download the utility. WebAssembly we'll get to. Let's do the more fundamental ones first. Let's look at, I guess, script and value. So there's two, I go back and forth intentionally between two different approaches when one thing depends on another thing. So you have script, which probably depends on values because there should be the values in the script. And so there's a question of, should you look at value first because you'll need it to understand script, or should you look at first to see how values are used so that when you look at value, you have a sense of like how is the API actually used in the way you want to understand it? And I kind of do both. But I find that often looking at them out of order is more informative, especially if you're getting a quick understanding. Okay, so in namespace v8, we have, we're going to refer to functions, class, objects, primitive arrays, and scripts. And then we have this like internal part of the namespace. We have a background deserialization task, script streaming data. We have V8 export. This is passed back to the embedder as part of host import module dynamically callback for module loading. Things like get ID, not so important. We have some status, uninstantiated, instantiating, instantiated, evaluated, evaluating, and errored. The different states that a module can be in. Okay, so these are at the module level, corresponds to the states used in ECMAScript, except that evaluated is split into evaluated and errored, indicating success or failure, respectively. You can get the identity hash, synthetic module evaluation steps. You can figure out whether we are in a synthetic module, etc. So this is just the header. We don't see the implementation here. So here this is, okay, so I guess the V8 export is some like annotation. So script compiler is that class script. So script has what? You can compile it, passing in the context, the source code as a string, and you get this as a result. V8, and, oh, no, you don't get this as a result. You get a maybe local script as a result. And you will warn if you're not used. And then I don't know what the script origin thing is, but it seems to be, I don't know if it's an in parameter or an out parameter. And we have this maybe local run. So you can run giving it a context, or you can run giving it a context and a host defined options. We don't know what local is yet. Local handle. So I'm guessing maybe this is the place where local is defined. Let's check that out. So we have class local base, a base class for local handles. Its implementation depends on whether the direct local support is enabled. When it is, a local handle contains a direct pointer to the referenced object. Otherwise, it contains an indirect pointer. We have local vector, local base. Class local. Where is it defined though? Let's try searching for class local. Is it in heap scavenger? And mark sweep. So it maybe it's related to the heap. Let's look here. Scavenger.h. So class local as this this local thing which takes a promotion list. You can push a regular object. You can push a large object. And the object is a tagged heap object. You can pop it, I guess, from the heap, from the position list, I guess. You can check whether the global pool is empty, etc. So let's go back to Gemini about de-optimization. The de-optimizes in scenarios where the assumptions made during optimization turn out to be invalid. This typically happens when the code's behavior deviates from what the engine predicted. Here are some common reasons. So the hidden class mismatch, incorrect type assumptions, function inlining. Okay. How about V8 JavaScript and local? We'll put local in quotes so that DuckDuckGo doesn't get rid of it. So it has something to do with embeddings. This document is intended for C++ programmers who want to embed the V8 JavaScript engine within a C++ application. A local handle is a pointer to an object. All V8 objects are accessed using handles. They are necessary because of the way V8 garbage collector works. Okay, so the handles may be some kind of, you might perhaps think of it as an indirection. It's a kind of container, I guess, that's visible or useful to the garbage collector that allows you to get it outside. Here we go. That's literally the next line. A handle scope can be thought of as a container for any number of handles. A handle scope is a container for any number of handles. When you're finished with your handles, instead of deleting each one individually, you can simply delete their scope. Okay, and a context is an execution environment that allows separate, unrelated JavaScript code to run in a single instance of V8. I don't know why it's called local, but local handles are held on a stack and are deleted when the appropriate destructor is called. These handles' lifetime is determined by a handle scope, which is, okay, so it's locally scoped, which is often created at the beginning of the function call. Okay, so that's about scoping, and that's why it's in the garbage collector. Here's the WebAssembly stuff. We have this compiled WebAssembly module, which you can do some stuff with. And we're just, it's not not interesting enough. Let's, I mean, it is interesting, but it's too technical to dive into in 7 minutes. So we're going to not look at it right now. So here's a V8 value. You've got a few classes here that are referring to primitive, numeric, big int 32, integer, number, object, string, uint 32. I don't see uint 36 or 64. And I wonder if these are essentially the objects we're working with. So everything is a data, a superclass of all JavaScript values and objects. We can ask if it's undefined, whether it's null. So I guess things are nullable. Is null or undefined. Is true. This is like, I guess objects can be converted or yeah, conversion to Boolean. Yeah. Okay. So this is, if you Booleanize an object, whether it's Booleanized to true or false, return whether it's a symbol, which is equivalent to type of value is triple equal to symbol, the literal symbol, is big int, et cetera, et cetera. So this is just kind of type information, and we have these like is predicates that we can call on things. You can try to convert things to a number, and so on and so forth. And what else do we have? Anything interesting? We have a type check witness. This should be, I guess, maybe a proof that the type check is as described, and be used to avoid repeated expensive type checks for groups of objects that are expected to be similar. For example, when Blink converts a bunch of JavaScript objects to script wrappable after it has instance check by making use of V8 internal hidden classes. Okay, so this is some sort of indication that type check has happened, and it can be used to shortcut type checking, it looks like. Here's WebAssembly. We haven't gotten into WebAssembly yet, and I don't know enough about it personally to make much sense of it, given the constrained amount of time we have. Here is Torque. I don't even know what Torque is. Maybe we'll just look up what Torque is. Torque. A V8 Torque. The language that it's a language, I guess it allows developers contributing to the V8 project to express changes in the VM by focusing on the intent of their changes to the VM rather than preoccupying themselves with unrelated implementation details. So I guess it's for trying to make it easy to translate the ECMAScript specification into an implementation on V8, but powerful enough to express the low-level V8 optimization tricks in a robust way. Okay, so that's seems like a nice tool for developers, is essentially what that comes to. Here's the V8 sandbox. We have a glossary. I don't think I've seen a glossary before. Move this chat out of the way for a moment. All right, so a sandbox is a region of virtual address space, typically 1 TB. I don't know if that's terabyte, containing all untrusted V8 objects. This is implemented as a large, contiguous virtual address space reservation using the appropriate operating system primitives. Address space reservations are cheap on all modern OSs. Okay, so a trusted object is one containing sensitive data or code located outside of the sandbox. You can expose trusted objects via pointers. A compressed pointer is a pointer that is guaranteed to point into V8's 4 gigabyte heap area inside the sandbox. So it's not only inside the sandbox, which I think it said was 1 terabyte, but also inside of the 4 gigabyte heap. These are stored as 32-bit offsets from the start of the heap area. They were originally developed to reduce V8's memory footprint. Okay. Then we have an uncompressed full pointer, which is a full 64-bit pointer into a heap object. These are regular raw pointers, which you get by decompressing them. And we have a sandbox pointer, which is just guaranteed to point into the sandbox. It's a 40-bit offset when the sandbox is 1 TB large that is added to the base of the sandbox when loaded. Okay, and then a protected pointer is a pointer that can not be modified by an attacker, only used between trusted objects. Okay, so these are various types of pointers and they have some guarantees. And I guess the guarantees are probably relatively easy to see how they're enforced. I don't know if there's any advanced wizardry, or if the wizardry is mainly in the design. The V8 sandbox, when enabled, V8 reserves a large region of virtual address space, the sandbox, and places most of its objects inside it. It is then assumed that an attacker can, by exploiting a vulnerability in V8, corrupt memory inside the sandbox arbitrarily and from different threads. And so this is more stuff about the sandbox here in the pointers. I think we can initialize it. We can check whether it's initialized. That we can get the size of the sandbox. We have a page allocator, returns a page allocator instance that allocates pages inside the sandbox, and so on and so forth. So this is cool. We'll see what else we can see. We won't look too much at the implementation of the sandbox itself. Here's the runtime. We have runtime array, atomics, bigins, classes, collections, a compiler, few texts. These are kind of standard, I guess, runtime-y things, similar to languages. I guess we'll look just at a couple of these. The runtime compiler. There's some logging stuff. We have this runtime function macro, and we're passing in runtime compile lazy. And we've got this handle scope stuff. This is like a assertion, essentially, decheck. And I don't know what all this stuff is. We're checking some stack limit stuff. Or maybe this is defining the runtime function via this macro. And maybe this is the name of it. And this is the implementation or something along those lines. Yeah, so I think that's what's going on. Here's runtime futex. This looks like more definitions. Runtime atomics, num waiters for testing. These are maybe runtime functions for handling the futex. Runtime scopes. These must be runtime scopes, and we're out of time. I am curious what maglev is doing here. Let's see if we can find out what's up in the header. We have maybe handle code compile. Maglev compile. How about maglev? Maglev is V8's fastest optimizing JIT. But why? Why are there two Google maglev projects? I don't know. But that's what they've done. And we're out of time, but here's the interpreter directory. There's some bytecode. We could look at the bytecode, but we're not going to. So execution, deoptimizer, compiler. We've seen lots of compilers, code gen, and we're just not going to get to it because that's life. So that's a little peek at V8. We're doing 30-minute time boxes until we reach the end of our backlog. And thanks for watching. Now we will move on to OpenFoam. Okay, so OpenFoam dev is the name of the repo. We're checking out the source code to OpenFoam, which is some sort of physicsy simulator for fluid simulations, I think. Numerical solvers for fluids, something along those lines. I am expecting it to be mathy and probably partial differential equation-y, and that's really all I know about it. I have seen some videos of OpenFoam in action. It looks super cool, but I just don't know much about how it's used or what's up. I don't know if it's used for special effects or if it's used for science, but that's what's the deal. We have some user guide here, C++ source guide. Oh, that's just the generated code. It does have a Wikipedia article. It says it's for development of customized numerical solvers and pre/post processing utilities for the solution of continuum mechanics problems, most prominently including computational fluid dynamics. It's used in research organizations, academic institutions, and across many types of industry, for example, automotive, manufacturing, process engineering, and environmental engineering. Yeah, we get a video. So here's some simulation. Maybe there is a video we can watch. And so there's some training. Here's a bathroom toilet. Should we watch this? Sure. Let's do it. This looks short. So I guess this is some simulation in OpenFoam. You've got the water in the tank. I guess it's starting to flush because we see the water is flowing down here. Accumulating in, maybe that's a P-trap. I don't know if that's officially called. I guess we're getting it rotating. I don't know if you model this mesh in OpenFoam or you import some modeled mesh from some other thing like Blender. And that's, I don't know what the red, the blue, and the green are. Maybe maybe it's like the amount of turbulence or something along those lines. Okay, so that's what OpenFoam is for. And let's dig into the code. I'll set a timer, 30 minutes. As I've mentioned in my other videos, we are sprinting to the end of the current request lists so that we may enter a new regime with a better, I think, approach to handling requests. But these are the requests that I promised that I would get to. And I want to make sure that I live up to my word. And so this one was requested on Reddit, I think. The only Reddit request that I've gotten. Okay. And if you want to, people ask me if they can request new videos. The way to do that right now is to join the Discord. You can find the link to the Discord on the video description. And on the Discord, we have a spreadsheet of potential requests, kind of a brainstorming spreadsheet, and that will seed the process for having the community choose kind of which requests to prioritize. But the status right now is I'm not taking new requests, but I will record the interest in a particular repo or a particular topic in that spreadsheet. Okay, so here's some bug just flew directly at me. All right, so here's the source file. We have ODEs, which should be ordinary differential equations. We have some sort of POSIX stuff. We have OpenFoam, a P stream, which is, I guess, relevant because we just watched the toilet. We have thermophysical transport models. I'm assuming that it has to do with transport in general. I don't know if thermophysical is the same as thermodynamic. We have atmospheric models. That's probably related to climate. Hello, friends of birds. Hello. I don't know what friends of birds means, but I support it. Combustion models, conversion. I don't know what we're converting. That might be something boring like file formats. That might be converting one sort of physical model to another. We have agglomeration methods, constraints, mesh distributors. FV. I don't know what FV stands for. Mesh movers, mesh stitchers, mesh topo changers, models, motion solver. So these FV things look like the sort of stuff you would see in Blender. They look like ways of dealing with and modeling 3D meshes. We have generic. I don't know what generic means. Lagrangian is either for computing with Lagrangians or dealing with a Lagrangian equation. We have mesh, which I'm going to guess is maybe the main model for mesh is like the base model. Then we have mesh tools and mesh check, which I'll ignore. Motion solvers, multi-phase models. Parallel is probably for parallel processing. Physical properties, that could be any number of things. I'm guessing that's just possibly attaching physical properties to the mesh. We have radiation models, topo changes, random processes, renumber, rigid body motion, sampling, species transfer, which sounds unnatural. A surf mesh is probably a surface mesh, thermophysical models, a tri-surface, maybe triangular surface, two-phase models, and waves. So this is way too much to get to. How are we going to start? I guess let's start with ODEs. We'll pop this out. I have a feeling ODEs might explode. We have solvers and systems, which is more interesting. We have the Euler solver in Euler SI. This might be familiar with, I guess, those of you who've used Stable Diffusion. They use the Euler solver sometimes. I don't know what ODE solver on its own is. This is probably some well-known solver. We get the OpenFoam documentation. A fourth order Cache-Carp Runge-Kutta ODE solver. So I remember Runge-Kutta from ODE class. And this is, I guess, the cache and carp probably improved on Runge-Kutta, which I think is super old. When is Runge-Kutta from? In numerical analysis, the Runge-Kutta methods are a family of implicit and explicit iterative methods, which include the Euler method used in temporal discretization. These methods were developed around 1900 by the German mathematicians Karl Runge and Wilhelm Kutta. Okay, so 1900. Wow. All right, so all of this RK stuff is must be Runge-Kutta stuff. Trapezoid is probably the trapezoid method for like numerical integration. Adaptive solver is probably some sort of attempt to do a smart solver. And I don't know what RODES are. RODES and Rosenbrock. How about RODES method? Construction of a multi-rate RODOS method for stiff ODEs. And then this just must be I don't know when to use these various methods. I guess we'll just pick out a couple of the methods, and then did we ever open the system? So ODE system, we just have the header and the C file, which for some reason is capital H header and capital C code. Why? I don't know. This is just some copyright statement, and Oh, look, we got a useful description as part of the copyright template. That's outstanding. So the class is foam :ODE system. And the description is it's the abstract base class for systems of ordinary differential equations. So what do we need? We need to know what the variables are. And we need to know what the equation is. And I guess what field we're in. Presumably over real or in complex fields. Not any sort of fancy prime fields. And we have this check thing, which is, I guess, doing some sort of check stuff. You can create an ODE system. And it's a system of equations. So you can have some number of equations. We have this virtual void derivatives. Calculate the derivatives in dy dx for the current state x and y. An optional index for the list of systems to solve li. Li? I don't know what Li is. We can calculate the Jacobian, which is basically just the matrix of second derivatives. And that's what we can do. Do we get PDEs? We have P delta. I guess, is it just too hard to solve PDEs? You just... Let's try OpenFoam PDE. Solving PDEs with OpenFoam. PDF. So the PDEs we wish to solve involve derivatives of tensor fields with respect to time and space. So what? There's some tensor stuff, but where do the... So we have equation discretization. So it converts the PDE into a set of linear algebraic equations where ax equals b and x and b are the vol fields. FVM is finite volume method. So I think we saw a bunch of FV stuff. That's probably finite volume solver. Let's ask the AIs. So OpenFoam, the OpenFoam source code has ODE solvers. And it so why only on ODEs and not PDEs? I think I'm probably missing something fundamental, like approximating the PDEs with an ODE. OpenFoam's core functionality deals with solving PDEs related to fluid dynamics and heat transfer. Here's why. There are a couple of reasons why they might include ODE solvers, so submodels within PDE solvers. Many CFD simulations involve submodels. Standalone ODE simulations. Okay. I don't know. Maybe we will see some PDE stuff. Maybe I'm just missing something, which is usually the case. Okay, so let's just take a quick look at some of these solvers. We have 20 minutes left. Okay, so maybe I'll also look at the system. There's a nice lambda, or nabla, I mean. Okay, so this check thing is going to evaluate the derivatives using the derivatives method, etc. I'm guessing just numerical derivatives, right? It's the only thing we implement is check, right? We've got check and what? Okay, here's df dx 0. I'm not really sure what's going on. Let's see if we can find other references to df dx. With this function derivatives, we go there. Let's try Emacs. Where we source ODE solvers. ODE system, right? Okay. So possibly defined in chemistry model. So derivatives takes a time, which is a scalar field, a label, Li, I guess Li is the label, in a scalar field, dyt pdt, and we do what? We check if we are a reduction, and then for all stoc I, we're going to set y stoc of I to the max of ytpi, else we'll do some stuff for y. I don't know really what's going on. We have some rho m thing evaluating a mixture density. I don't know if that's mixture density in the sense of a probability thing. Species thermos. Something. Some sort of, we're looking at reactions. All right, I'm not sure. I'm not sure what's going on there. What about this df dxe thing? No definitions for that. What about scalar field? We have primitive fields. We have, okay, so these are, a field of scalars is a scalar field. That makes sense. What is a field? We have field.c. A field is just like a list. Okay. That tells us a little bit, but I feel like I have more questions than I have answers. Let's return to solvers. That's ChatGPT. That's Emacs. I think this one. Okay, so ODE system doesn't seem to have much there. Actually, let's open that back up. Oops, not that. And let's see if we're importing anything, including ODE system.h. I guess this gets implemented somehow as other things. So the ODE solver Euler.h has what? We have a type name, Euler. We can construct one, we pass it in an ODE system in a dictionary. I guess the dictionary maybe has the like values of the variables or something along those lines. Inherit from the ODE solver. Resize the ODE solver, I don't know what that means. And then we have this solve thing. Solve a single step dx and return the error. So we are going to, oh, these are just we're in the header, so this is just the arguments to solve. And so on. So let's see what the implementation looks like. And solve will, for all error underscore I, calculate error estimates from the change in state. So we're going to take dx, multiply by dy dx 0 at I guess dy dx 0 is a vector, or I guess it must be a vector. It's not a matrix. And that's going to give us an error underscore at I. And then we'll update the state by setting y sub I to equal y0 sub I plus error at I. And then we will normalize the error. And then that's what? That's Euler solve taking in a bunch of arguments. Is this just fewer arguments? We call adaptive solver here. If we pass it in what? I'm not sure. So it looks like we're maybe passing in less stuff here. And we're using adaptive solver as opposed to the Euler solver, although this is Euler. And in this solve function, we are passing in dy dx as a scalar field, which is just a list. And so all the stuff we need for calculating this stuff is passed into the function as opposed to being computed by the function. Okay, fair enough. And then here's the generic ODE solver. I don't know what solver L is. an abstract base class for ODE system solvers. And what? We have some ODEs. We have abs2L, absolute convergence tolerance per step. So this is somehow configuring, I think, the convergence. And we have a step state, which is a class, although it's started in lowercase, which is a little bit unconventional, but it doesn't matter. And we have a Boolean for forward, maybe whether this is a forward step as opposed to some other kind of step. We have dxtry. I'm not sure. I'm not sure what this t stuff is. This is some change in x, try. I'm not sure. Did. I'm not sure. And then first, last, reject, pre-reject. I guess with it to reject the state. And then step state called on a scalar dx. Okay, so we're going forward if dx is bigger than 0. And dx try and did. Maybe I was thinking of this as something in the physical model, but I'm wondering if this is like we're going to try this dx. This is the dx that we ended up with, perhaps. And then whatever this first, last, reject stuff is. Let's look at the implementation. That's resize. This is what? Sort of constructor it looks like. So solve of x, y, li, dx try is going to, we're going to call step on dx try to get a step state. We're going to solve with maybe this, I'm not sure what's going on here, but we're passing in, I think we're passing in the thing we did here to solve. And we're setting dx try to be whatever is in step dx try. Where's the step function? Let's head back to Emacs. No definitions for step. So we have step state, step.dx try. I'm not sure what step is supposed to be, like what type it is. I guess steps, we're just declaring the step is of type step state, right? Yeah, okay. So it's some state. And here's the solve thing. So we're creating this state with whatever dx try is. We're going to set x to the start, x start, and then we're going to iterate over the labels. I guess we're going to iterate over steps. So end step is 0. Well, this is confusing. This confused me. This is just checking if end step is less than max steps, but it looks like this is the beginning of like a templating thing. And then we're incrementing end step. I don't know why we're using a label. We're going to store the previous iteration, dx try. That's going to be dx try 0. 0 I thought would have meant initial, but this just seems to mean previous. We'll set step reject to false. Check if this is a truncated step and set dx try to integrate to x end. So if x plus step dx try minus x end times x plus step dx try minus x start is bigger than 0, then we'll set step last to be true. So I guess we were at the end. And dx try is the difference between x end and x. And then we'll integrate as far as possible up to step dx try, calling solve on X, which we maybe adjusted here, and step and LI, which I think is some label. They're calling it a label, but I think it's an index. Into something, into what, I'm not sure. Maybe into which equation in the ODE. Maybe check if we've reached the end. We'll set step first to false, and if we reject, we set step previous reject to true. And there might be some error. Okay, so that's some implementation of solving. I find that I'm a little bit not used to the style of C code, so I'm getting a little bit mixed up on the syntax here. All right, so what else do we have? So that's IDE solver. It kind of looks straightforward from a numerical solver point of view, modulo me getting confused about the syntax and whatnot. This is the root directory. We don't need that. This is some directory we don't need. pstream. I'm not sure what pstream is. We have MPI. And this make and clean, I'm going to guess, are like new make files. These are scripts. wmake is maybe some make system. Maybe specific to OpenFoam. MPI, I think, is the message passing interface for like high performance computing. upstream. Valid parallel options vary between implementations. So this is like use parallelization for solving, I guess, some of these models. Thermophysical transport models. Let's pull this into its own tab. We have fluid, coupled thermophysical transport model, fluid thermo, phase fluid, multi-component thermo. These, I don't know how all of these differ. With any like scientific enterprise, there's going to be like closely related models with slightly differing assumptions depending on the problem you're trying to solve. I don't know the extent to which the names that they've chosen are like industry standard names, or if they're just kind of like custom OpenFoam names as they're trying to figure out where each thing goes. Here we are in fluid, and we have laminar, which is like, I'm guessing, modeling a fluid with laminar flow, turbulence, presumably modeling a fluid that has some turbulent flow. Phase, thermophysical transport model, derived FV patch fields, and so on. We'll just peek through some of these and try to get a sense for what is life like as an OpenFoam developer. Fickian Fourier. So this is laminar. Maxwell Stefan. Let's look up Fickian. So this is related to Fick's laws of diffusion. From 1855. So there's some diffusion coefficient. The first law, movement of particles from high to low concentration. Diffusive flux is directly proportional to the particle's concentration gradient. And the second law, prediction of change in concentration gradient with time due to diffusion. Okay, so this is classic stuff. Fourier. I'm sure Maxwell Stefan is maybe James Clerk Maxwell. This seems to be, I think we figured out laminar flow much earlier than turbulent flow, which I don't think we've figured out even. I think is in general an open problem. So we have some eddy stuff. Eddies are little turbulent curly things and so on. This is turbulence. Here's fluid in general. We have a phase thermophysical transport model. Let's look at that. It's a templated base class for multi-phase thermophysical transport models. I don't know what multi-phase means. I don't know if we're like changing like phases of matter, or if we're maybe changing from laminar to turbulent, or both, or all three. We have a momentum transport model, a thermo model, and a momentum transport model alpha field. We have some constructors. And I don't know. Let's look up thermophysical transport model. We may end up back in OpenFoam. Thermophysical models. They're used to describe classes where thermal energy, compressibility, or mass transfer is important. OpenFoam allows thermophysical properties to be constant or functions of temperature, pressure, and composition. Thermal energy can be described in form of enthalpy or internal energy. The relation can be described with various equations of state or as isobaric system. The Thermophysical Properties Dictionary is read by any solver that uses the thermophysical model library. A thermophysical model is constructed in OpenFoam as a pressure-temperature system from which other properties are computed. There is one compulsory dictionary entry called thermotype, which specifies the complete thermophysical model that is used in the simulation. And so this seems to be, let me see if this is any more readable without Dark Reader. Sorry for the brightness, and no, it's just about the same. But this looks like maybe this is generated documentation. And so this is useful. I guess this is probably all in the code as well. We have some equation of state is an with an ICO polynomial, which is an incompressible polynomial equation of state, e.g. for liquids. So it's polynomial. I forget what incompressible means at the equation level. Perfect gas is a perfect gas equation of state. I don't know if these are two types. Then we have basic thermophysical properties like a constant specific heat model. Or maybe these are types of models. I'm not really sure what we're listing here. Various combinations are available as packages, specified using, for example, thermotype. Type is E-rho thermo. Mixture is pure mixture. Transport is const. Thermo is H const. Equation of state is perfect gas. Species is species. And energy is sensible enthalpy. And then we have a mixture, which I guess is setting species to mole, maybe molecular weight, 28.96. Thermodynamics, CP and HF. I forget what they are. I guess these are, I don't remember. And transport, mu is 1.831 times 10 to the negative 5. And PR, maybe pressure, is 0.705. So these are ways of, oh, here we go. Species, containing, i.e. number of moles and moles of the species and molecular weight in units of grams per mole. So mole is the moles as opposed to so mole weight, I guess, is the weight of a mole as opposed to the molecular weight. Thermo is containing coefficients for the chosen thermodynamic model. Transport is containing coefficients for the chosen transport model. Thermodynamic coefficients are ostensibly concerned with evaluating the specific heat. Yeah, so that's what this was, right? Somewhere. Or maybe not. From which other properties are derived. The current thermo models are described below. We have H const thermo. Assumes a constant CP and heat of diffusion, and a heat of fusion, HF, which is simply specified by two values, CP and HF. E const thermo assumes a constant CP and a heat of fusion. These are both constant in a heat of fusion. CV. I don't know if like CP is like position and this is velocity. I don't know. Okay. So that's actually an interesting and useful page, but I'm not going to read all the way through it. I think we're technically out of time, but I'm going to keep going because I'd like to see some more of this repo just to understand a little bit about what we're doing. Here's derived FV patch fields. So what do we decide FV was like finite volume? Derived, I don't know if this means that we've taken a derivative or perhaps these are just derived in the sense that they come from some other patch field or finite volume thing. We'll just peek inside one of them at random. The class is this thing, external coupled temperature mixed FV patch scalar field. These names would make Java programmers envious, I think. And the description is this boundary condition provides a temperature interface for an external application. Values are transferred as plain text files where OpenFoam data is written. So I guess we're using text files as a medium of transfer And maybe that's related to using MPI. That means, I guess, if we interpret it totally literally, we're like writing to disk, which doesn't seem like the most optimalist thing, but I don't know. I don't know if that's actually what we're doing. Provides a temperature interface to an external application. I'm not sure what that means. And we receive as the constituent pieces of the mixed condition. For example, value 1, gradient 1, value fraction 1. Data sent and received as a single file for all patches in the directory. So I guess this is a patch maybe of a model, of a finite element model, and then we are sharing it with other nodes so that the different patches can be solved independently on different nodes in parallel and then stitched together, I think is probably what's going on. So let's see if we can pull a diagram of the finite volume method. The finite volume method is a method for representing and evaluating partial differential equations in the form of algebraic equations. In the finite volume method, volume integrals in a partial differential equation that contain a divergence term. This is divergence in the calculus sense, I assume. Yeah. Are converted to surface integrals using the divergence theorem. These terms are then evaluated as fluxes at the surfaces of each finite volume. Okay. So we're just using the fundamental theorem of calculus, really. Because the flux entering a given volume is identical to that leaving the adjacent volume, these methods are conservative. Another advantage of the finite volume method is that it is easily formulated to allow for unstructured meshes. It's used in many computational fluid dynamics packages. Finite volume refers to the small volume surrounding each node point on a mesh. This you can contrast with finite difference. So for example, consider a simple 1D advection problem. Given by that, blah, 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 integrating, blah, blah. That's all fine and good. That's math. What I'm more curious about is how this parallelizes. And I think I was implicitly confusing it with the finite element method. And in the finite element method, we subdivide the whole domain into simpler parts, having several advantages, blah, blah, blah. Let's see if this mentions finite volume. I mean, yeah. Generally, FEM, the finite element method, is the method of choice in all types of analysis in structural mechanics, that is, solving for deformation and stresses in solid bodies or dynamics of structures. In contrast, computational fluid dynamics tend to use FDM. I don't know what the D is here, or other methods like finite volume method. Okay, so what is FDM? Finite difference. Okay. So we're doing finite volume as opposed to finite element. That's all fine. And this is somehow this patch scalar field is some way of cutting up the volumes, I think, and sharing them with other machines. Here's a fluid thermophysical transport model. This is the abstract base class for fluid thermophysical transport models, RAS, LES, and laminar. I don't know what RAS and, what was it, LES are? You use the class. And I think there's not much interesting in the header. Let's see if there's anything much interesting in the C file. Not really. You've got this label patch I, which I'm guessing the label, they use labels for like indexes. I'm guessing label is just typedef as like an int. Yeah, a label is just an int. So I guess we're just keeping track of which patch we're on. And so that's a thing we can share with other nodes. And what else do we have? So here's fluid thermophysical transport models. The names are all really similar. I don't know the difference between these two headers. Model versus models. one is plural. I guess probably the plural one is a container. So this file we get includes, so we're including some laminar models like Fourier.h and the Unity Lewis Fourier, and also RAS models like eddy diffusivity, which is what's the word? Non-laminar, turbulent, and also LES. I don't know the differences between all of those, but those are things that we're including. Here's fluid multi-component thermal. I'm going to guess that I'm going to guess that's not so informative. Let's look at this one. I'm going to guess this is similarly not so informative. These are type defs for laminar, RAS, etc. These are all type defs. Is there anything in the C files? I'm finally getting a feel for like how the code is laid out. Okay, so these thermo whatever Jim will call it models are not so. These files are not so important. Just for the sake of thoroughness, let's check this folder. This is some new function that'll create one, some kind of model. And we've got an iObject IO dictionary header with a group name, some thermo mesh stuff, timing, must read, no write. If the header is okay, and we'll look up something in the dictionary, looking up the model. And I guess this is like, seems like we're working with a file. And we'll somehow grab an iterator and check if it's equal to the dictionary, constructor, table, pointer. End. I guess the end of the pointer. And we'll, if so, I guess we will error out because somehow the iterator got to the end of the thing it wasn't supposed to get. It says unknown solid thermophysical transport model. Otherwise, we'll return an auto pointer of phase solid thermophysical transport model, taking the thing we get from the caster iter and passing in alpha and thermo. So I think essentially we're reading some file and possibly also writing files. Okay, so no more models. I'm done with models. Here we are in Fourier. This is maybe actually doing some math. Fourier's temperature gradient heat flux model. Simple species laminar flow. Heat flux source is implemented as an implicit energy correction to the temperature gradient based flux source. At convergence, the energy correction is 0. So it sounds like when we have converged, the energy correction is 0. I don't know if energy correction 0 is how we determine whether we've converged, but maybe we will see it in the implementation. So we have some class Fourier, and this syntax is really throwing me off. It's extending some model. It's extending a laminar thermophysical transport model templated by basic thermophysical transport model. And we'll define some types. We'll declare what the type name is. You have a constructor, you have a destructor, and some member functions. Coefdict is the dictionary of coefficients. We can read the dictionary, or that returns a bool. Maybe this is whether we can read the dictionary. The effective mass diffusion coefficient for a given species mass fraction is some temp. Why is it temp? I don't know, but some temp vol scalar field. Vol maybe volume. D, E, F, F. D, E are capitalized. Not sure why. And I'm not sure really what's going on there. We also have this other temp scalar field thing, effective mass diffusion coefficients. These are 2 coefficients. More temp stuff. Everything is temp. Why? I'm not sure. Let's take a look at the implementation and see if we just see anything interesting. So each of these functions, I guess, gets a fatal error function I'm not sure if we're just setting the fatal error function so we can essentially return it or print it if an error happens. And yeah, I don't know. And then here, what is this? This is some model. This is some function Q, which is going to, which is templated. This should be the return value. It's returning some version of a model, and it's calling whatever FVC is, finite volume compute something, and we're interpolating with alpha times thermo.kappa times FVC SN grad. Grad, I'm going to guess, is gradient. SN, who knows? Passing in thermo T, and we're taking the negative. This is some group name. Maybe this is just metadata. And, or rather, we're returning a scalar field with this is the second value. This group name thing is the first value. And the name of the thing is Q. So that's probably some coefficient in the equation. And so on. So there's like a mix of computation here and also like metadata and so on and so forth. I still don't know why everything is temp, but I don't know why a lot of things are the way they are. Maybe TMP stands for something other than temporary. Here's Maxwell Stefan. This should be pretty similar, I think, in spirit. We have an array of species binary mass diffusion coefficient functions, which are dfuncs. And then we also have DT funcs, which are the Soret thermal diffusion coefficient functions. I don't know what they are. I don't know what species is. Species fluid dynamics, or maybe it's about thermodynamics. Computation fluid dynamics. Okay, so single species means it consists of one chemical species. I don't know what a chemical species is. Chemical species are a specific form of chemical substance or chemically identical molecular entities that have the same molecular energy level at a specified timescale. These are classified through bonding types and relatively abundance of isotopes. Types of chemical species can be classified based on the type of molecular energy, molecular entity. It can be either atomic, molecular, ionic, or radical species. Table salt is an example of an ionic species that is composed of the chemical formula NaCl. Okay, so that's what a chemical species is. It's, I think, maybe from the perspective of this software repo, the species, the fact that it's one species tells you that it can be kind of modeled with similar equations. And then when you change species, it seems like you change maybe how you model it. This is more transport model stuff. I'm going to guess there's not much there. Eddy diffusivity. I'm just mildly interested in seeing whether this is different enough. We have some momentum transport stuff. We have rho and nut. I don't know what nut is, and we're dividing by PERT. I don't know what PERT is, but I don't think we've seen momentum really yet. Before, I don't think we've really seen much about boundary conditions either, although we may have, and I've just glossed over it. So this is some model, and we feed it a momentum transport model and a thermo model. And PERT is dimensionless, I guess, and we have some coefficient dictionary and some alpha T. And I guess the thing that we're defining alpha T as, alpha rho phi group, I guess it's like alpha at time T. And we have some, I guess we're passing it some momentum transport mesh. All right. This is more different models. Don't do that. And what, so we have some, so this is atmospheric models. I'm going to guess these are all kind of similar to look at code-wise. You have vector scalar fields. I mean, the thing that's going to be different about them are going to be that the ODE systems are different. The code is really going to look the same. Combustion models. There's lots of different kinds of models. No combustion, radiation, diffusion, combustion, PASR. Conversion. This seems to be for converting mesh stuff. I don't know what an agglomeration method is. Oh, maybe agglomeration is like stitching patches together. Pair patch agglomeration. Let's see if we can find anything about it. Primitive pair patch agglomerate method. Let's look in the documentation. So maybe it's a form of coarsening. Operation coarsens using agglomeration. This is what? This is the GAMG solver. Using agglomeration, so face area pair, geometric and algebraic pair, numerical coefficient. Agglomeration, number of levels depends on number of cells at coarsest level and hard limit of a maximum 50 levels. So I think we're maybe combining nodes in some way. Here's face agglomeration. Agglomerate boundary faces using the pair patch agglomeration algorithm. Writes a map of fine to coarse grid. So I guess you have the fine grid is the you have some mesh that's fine, and you're trying to make a coarser mesh, like a low. In graphical terms, it might be similar to making a low poly version, so that presumably the algorithm runs faster on the coarser version. Distro. You're asking me which distro this is? This is Linux Mint, I think. Yeah, Linux Mint. So this window manager is Cinnamon, if that's the question. All right, so that's what agglomeration is. This should be some algorithm for matching up faces of the mesh that are close to each other and combining them into a single face. This is constraints. Limit temperature, limit pressure, mean velocity force. Let's look at limit temperature. I don't know how these constraints are implemented, but we have some optional field, which is the energy temperature field name. The type is limit temperature. The phase is gas. Oh, this is just an example usage. Okay. So you can say that the phase of this object that you're modeling is gas. So we saw at the beginning a model of a toilet, which uses water, which is liquid. And I guess the minimum temperature here is 200 something or others, not Kelvin, probably Celsius, and the max is 500. And then I don't know what actually enforces the constraint. So the constrain function which is a Boolean, so I guess it's going to return whether you successfully constrained it. So we have a label UList of cells. Maybe this is like the UV decomposition. No, what's it called? Something. UV mapping. You want to guess? Something like that. I don't know if that's what the U is for. Uh-oh. I don't think I can get that back. I can. So we have the cells, and we check if the dimensions equal the temperature dimensions, I guess. If they don't, there's probably some error. No, we have some other algorithm that runs if the dimensions are not what we expect. And we get a primitive scalar field. No, we look at HE, which is the vol scalar field we passed in, and we get its primitive field ref. This is probably a pointer to some object contained in the vol scalar field. And for all of the cells that we got from the set, I'm not sure where the set came from, then we are going to take cells at I, taking this vector or container and taking this element, getting an element, and then setting here TC at cell I. I don't know why we needed to create a new variable. And we're going to set it to the maximum of, okay, so this is just clamping between max and min. Okay, so that's how it's enforced. And then if the dimensions don't match up, then we do something else. What do we do? I'm not sure. Where's the else condition? Else. You do some sort of mesh lookup group name. And we have a min and max field. And we have some boundaries, I guess, to consider. All right. Then we have mesh distributors, a load balancer. Maybe this is for distributed in the sense of we're distributing the computation. Dynamic mesh redistribution using the distributor specified in decompose predict. CPU time. Yeah, so this is distributing, I guess, the meshes among nodes of a computer cluster, I guess, for solving. A mesh mover, we have inkjet, interpolator, motion solver. What is inkjet? Specifically for the pumping system of an inkjet injector. I guess this is for modeling the inkjet. And we have a motion solver. Maybe this is you give it the equations of motion or something along those lines. A motion blah, blah, blah. Do you get a comment? Well, at any rate, a motion solver has, whether it's a solid body, an update function, some update the corresponding to the given map, some ability to change the topology. We have map mesh, update from another mesh using the given map. We can distribute, I think, in the sense of distributing to machines, and we can write. I don't really know what that does. Something about distributing in motion. We have topo changers. I'm going to just really plow along. There's nothing interesting in the make file, is there? No. Okay. Displacement. Let's look up OpenFoam motion solvers. I just kind of want to know what they do. Standard solvers. Based on solving the cell center solid body rotation stress equations for the motion displacement, the model calculates the necessary rotation to align the STL surface with the closest mesh face normals, and it calculates the respective source term for the SBR stress equation. So I'm not sure if this is for like internal use for OpenFoam to figure out like the physics by rotating the mesh and solving stuff about mesh rotation, or if this is for modeling objects using the equations of motion. So we get some inheritance diagram, and I'm not sure I don't think there's enough here in the documentation to tell that to me quickly. Here's generic. We have generic fields, generic patches, generic field base, generic point base. And so we're way over time, so I'm just going to see if there's anything that I really want to see. So Lagrangian, this seems like maybe a pretty fundamental thing. A parcel, what is a parcel? I'm guessing it's a piece of a mesh. Include derived templates, parcel packing models, parcel injection models. I don't know. Clouds, templates and derived. So a colliding cloud, a spray cloud. Let's look at spray cloud. Spraycloud.h. Templated base class for spray cloud. Submodels, atomization model, breakup model. We have a cloud type. The type of parcel the cloud was instantiated for. References to the cloud submodels. We have an atomization model and a breakup model. So I guess this is how things are atomized and how things are broken up. And we can construct the spray cloud. Let's look up OpenFoam Lagrangian. This is Lagrangian solvers. So Lagrangian solver. What is a Lagrangian solver? I think Lagrangian is the kind of equation and not the kind of solver. Lagrangian function. Used to, maybe using Lagrange multipliers used to solve constrained minimization problems in optimization theory. The Lagrangian submanifold in symplectic geometry, I don't think it's that. Lagrangian system, a fiber bundle, and Lagrangian density. I don't think it's that. Lagrangian and physics. Oh, this is maybe, yeah, the physical Lagrangian. I don't know if it's the field theory Lagrangian. No, it's just, the field theory Lagrangian is just the field version of the Lagrangian mechanics. I'm guessing this is maybe Lagrangian in the sense of Lagrangian mechanics. That we specify a Lagrangian physical system. A transient solver for compressible turbulent flow with coal and limestone particle clouds. An energy source and combustion. More. Do we not get more? Here's the source code. Limestone parcels. So parcel, I guess, is some like collection of volume containing limestone or something along those lines. We have a pressure velocity PIM PLE loop, corrector loop. And while the loop is going, the do includes. And while it's correct, we do more includes. And if the turb core, I don't know if this is like turb, I am guessing turb means turbulent. Core, maybe correlation or correction. Oh, okay, maybe correct. So turbulent, then we call turbulence correct. And we set row to thermo row. We call runtime right. And we call print execution time. So this looks like it's actually doing work. We looked up Pimple before. Let's see if I can remember what it is. I don't remember. Is it pointer to implementation? Okay. This technique used for separating implementation from the interface. So we have the for declaration of the implementing class, and then the const forwarding pointer wrapper unique ownership opaque pointer, and so we're wrapping a unique pointer to the implementation, the forward declared implementation class. Because private members of a class participate in its object representation, affecting size and layout, and because private member functions of a class participate in overload resolution, any change to those implementation details requires recompilation of all users of the class. Pimple removes this compilation dependency, changes the implementation to not cause recompilation. Consequently, if a library uses Pimple in its ABI, newer versions of the library may change the implementation while remaining ABI compatible with older versions. Okay, so that's useful to know, and that's what's going on. Okay. So that's Spray Cloud. I feel like the Lagrangian folder so far is where all of the action is. Unfortunately, we are just way over time, and I'm going to just get out of here. So this is mesh stuff. We haven't looked at any of the mesh stuff. We looked very quickly at mesh solvers, but we're not going to do that. And we have multi-phase models. We'll ignore that. Parallel processing, I think, is probably about processing over different machines. Physical properties we haven't looked at, but we have viscosity, physical properties as a folder on its own. And there's not much there in the header. Thermophysical properties IO. I don't know what that is. I don't really see a list of like which properties we're dealing with. I don't know why viscosity gets to be a physical property, but like temperature doesn't. But that's what that's what's going on. And we have some model of viscosity with new. I don't know really what this is presumably related to the viscosity equation. I don't know much about viscosity or really any of the physics stuff here. Now we have polytopo change. This is something about changing the properties of the topological, whatchamacallits, radiation models. Scatter model. You know what? I was originally thinking this was like radiating like out from the center, but I think this is like radiating in the sense of electromagnetic radiation. But maybe we can take a check. This is the top level model. We have some scalar fields, a dictionary, a solver, stuff. Declare runtime selection radiation model. I can't really tell. Random processes. K-mesh, OU force, FFT, maybe fast Fourier transform, noise, and turbulence. So those are all random processes. You probably literally need a random number generator for it. Rigid body motion should be just three-dimensional motion that doesn't deform the mesh. We've seen some of that in game engines. Sampling is sampling, but we're not going to look into it. Species transfer. I don't know enough about species to know what they're going to do there. Here's thermophysical models, which we've seen lots of models, and I don't think that they're super informative. Error loading page. About mass fractions. Yeah, okay. The tri-surface is some sort of triangulation surface. A two-phase model. We have things like compressible cavitation, compressible two-phase, interface compression, two-phase mixture. I'm guessing phase is maybe like, I don't know what VOF is. Is maybe like phases of matter, or where the physics change so fundamentally from one thing to another. We also have waves, which we're going to ignore. Random processes we'll ignore. Noise, I think we just opened up, but we're going to ignore. VOF has something to do with alpha controls. There's VOF physics. Or maybe VOF OpenFoam. The breaking of a dam. So VOF method. Volume of fluid method is a family of free surface modeling techniques. That is, numerical techniques for tracking and locating the free surface. They belong to a class of Eulerian methods that are characterized by a mesh that is either stationary or is moving in a certain prescribed manner to accommodate the evolving shape of the interface. They're advection schemes capturing the shape and position of the interface, but are not standalone flow-solving algorithms. The Navier-Stokes equations describing the motion of the flow have to be solved separately. Okay. So free surface modeling, I'm not sure what exactly that is. They're numerical. Locating the free surface or the fluid-fluid interface. Okay, so I guess we have two fluids and there's some interface between them and it's moving over time perhaps, and we're trying to figure out like where it is. So I don't know what this is. Maybe these are two. This is, I guess, a ball dropping into a fluid and then it makes a splash. This is a splash, I believe. So free surface modeling is the numerical modeling of a free surface, a freely moving interface between immiscible fluids. Okay. So zero parallel shear stress, such as the interface between two homogeneous fluids. Okay. So two immiscible fluids, and they make some sort of boundary or surface with each other. This is compressible cavitation. I'm not sure this we're really going to learn anything from here, although we have Merkle. I doubt this is the same Merkle as the cryptographic Merkle. Merkle cavitation model. I'm just curious. Let's just open up a PDF. We're not going to get the whole full PDF. Evaluate the applicability of mass transfer cavitation models. Cavitation is like the creation of a cavity, I think. Cavitation in fluid mechanics and engineering normally refers to the phenomenon in which a static pressure of a liquid reduces to below the liquid's vapor pressure, leading to the formation of small vapor-filled cavities in the liquid. When subjected to higher pressures, these cavities, called bubbles or voids, collapse and can generate shock waves that may damage machinery. You don't want that. Okay. So that's what cavitation is, and that also explains why we want to solve for them in OpenFoam. So that's OpenFoam. I'm not going to look at OpenFoam anymore. It's clearly a cool project. My only take on the code is that there's so much of the code is like bookkeeping. It was kind of hard to find where the physics is. In the times when we did find the physics, you would only see like a little bit of physics, and then you would probably have to like chase it down. And it's just kind of it's not organized in a way that really makes, I think, reading it super easy. There may be reasons for that. It may be that I don't know what the reasons would be, but it could just be that this is a project that kind of spans between the academic world of physics and to some extent numerical computation, and industry. And so a lot of cases code like that is written in a very different way than you would see like in industry. So to me, it would be nicer to have like a clearer separation between like, here are the physical models and here's like the code for that we need for spreading out computations and having like real clear places in the source code for where to find those things. Because, for example, if you wanted to like make a change to how if I wanted to make an optimization for some solver, it's not entirely clear like at what level to make that optimization. It seems like I might have to dig through a bunch of different things. It's not clear if the optimization can change depending on the model. Like there might be some types of physical models where you want to tweak the solver one way, whereas in another type of physical model, you want to make a different optimization. I don't know if that's a useful thing to do. And if it is, I don't know like how possible it is with this code base. I found it a little bit disorienting from a reading point of view. Some of that might be less disorienting if I were more familiar with computational fluid dynamics, but it just seemed to me like we were 95% of the time kind of looking at metadata as opposed to behavior. It's just my sense. And Raju is asking me to give them $9. No. But if you want to give $9 to the Holy Hedge Fund, you can do that through the YouTubes. Okay, so we've been live for a while. Two hours, 40 minutes. Part of me wants to do one more. And what I have of the request is it just says HTTP/S. And I wrote down where I got all of these requests from, and I don't have an annotation of where this came from. I think this might have been like while I was live at some point, and it's not something searchable. So the way I've interpreted that is one of the classic HTTP servers. And so let's get rid of OpenFoam and V8 and Clojure here. And we'll just take the smaller of Nginx and HTTPD. Which is Nginx. Although some of that might be the Git history. How do I just delete Git? It's still Nginx. All right, so let's look at Nginx. And we'll do 30 minutes for real this time. So I guess it's really in a Mercurial repository. Today, we will peer deep inside the heart of the HTTP server that runs much of the internet. We're going to look at the source code for Nginx. And we're going to spend only 30 minutes doing so. As I've explained on some of my other videos, I'm not taking requests right now. Requests are paused. If you want to make a suggestion for a future video, you can join the Discord. The link is below. And you can add your suggestion to the spreadsheet. I'm not promising to get to any of those, but that will serve as the brainstorming inspiration for the user requested videos in the new regime, which happens once I finish my current backlog. And I think all of this stuff is going to be in source. So we'll go to nginx/source, and we see core, event, HTTP, mail, MISC, OS, and stream. The request was that I look into HTTP. So that event is going to be presumably some sort of event system, maybe an event loop for handling requests. But my mandate right now is to look into HTTP, and so that's where I will be. So Ngx, I'm guessing, is just the prefix that means Nginx. And what do we have? Well, we have a parser. Do we have a header for the parser? Maybe the headers are in another folder, although they don't seem to be because we have several headers here. Just not everything has a header. We have a core module. I don't know really if module is necessary. We're not going to look at file cache. I really want to focus on the protocol if I can. This is presumably Huffman encoding and decoding. We open the parser. What else do we have? Maybe request and request.c, request body. Script, perhaps. Upstream, I'm not sure if that's interesting. Variables, I'm not sure if that's interesting. And maybe that's enough for us. So HTTP parse. We have a usual vector here. I don't know what this is. This is some hex codes. And I don't know why I keep disconnecting. But let me check one thing. Yeah, okay, good. Okay. I'm not sure what these are. 1111111, 1110, 11111, and more similar. And some of these are the same. We have a lot of OX and then a bunch of Fs. We have this stir3 comp, which takes M, C1, C0, C1, C2, C3, And we're checking if M cast as a UN32 is equal to this C3 shifted by 24 or a C2 shifted by 16, et cetera, et cetera. And this, I guess, only happens if we have little endian and have non-aligned. So this is somehow maybe, I forget what the endianness of the network is. Endianness is primarily expressed as big endian or little endian. Blah, 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 and network, blah, the term, blah, 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 blah. But which one is the internet? Big endianness is the dominant ordering in networking protocols, such as in the Internet Protocol Suite, where it is referred to as network order. So, okay, so big endian is network order, and conversely, little endianness is the dominant ordering for processor architectures and their associated memory. Okay, so I think this is maybe converting between big endian and little endian, although why it's called comp, I'm not sure. But we probably will see these used somewhere. I don't know why stir 8, stir 9. And then if we're down here, then I guess we don't have these two things. We don't have little endian and non-aligned. In which case, these comparisons look a lot more straightforward. We're checking if M0 is equal to C0 and M1 is equal to C1 and M2 is equal to C2. Okay, so we are checking, we have M, which is like a list that we can index into, and we're checking if its entries are C1s, C0, C1, C2, and C3. And up here, we're like compensating for the endianness and I guess doing the same check. And we're ORing these together because we are shifting the bits over. Okay. Then we have a comment here. GCC, ICC, MSVC, and others compile these switches as a jump table. So you've got this function Nginx HTTP parse request line. You give it an HTTP request, or rather a pointer to one, and an Nginx buffer. And it's going to return you an int, an Nginx int, but I assume it's really just an int. So we have these UCARs, which I guess are unsigned cars, C, CH, P, and M. I don't know what these are going to be, but we have some enum. Looks like we're defining this enum in the function. So SW start, SW method, SW schema, switch, I guess. Spaces before URI, HTTP 09. I don't know what this stuff is. That's the state. And we'll set state equal to our state, the state from the request. So I guess this is coming in as part of the HTTP request. Let's look up the HTTP state. Is it the same as XML HTTP request? Probably not. Let's look up the HTTP header. The standard request fields are these: accept encoding, cache control, content length, cookie, expect, post. I don't know if there's a state. I don't think there is. So, well, there's this. There's cookie state, but I'm not sure. I don't know what HTTP 09 is, for example. What is an HTTP 0.9 request? is a one-line protocol. Its main points are initial version of HTTP. Okay, so this is, I guess, the initial version. Request nature, single line, method plus path for requested document. Only supports GET. Response type is hypertext only. Connection nature terminated immediately after the response, and no HTTP headers. Where's the spec? Not the spec. Is this 1992? All right, whatever it is, it's I think it's the oldest HTTP spec. All right, so that's whoa. That's what that is, I guess. These are different things that are in the request. I don't know where request.state gets set, but it's set somewhere. And then we iterate over P as being used as like an index or a pointer. We get the B position as B the body. That's the buffer. We're going to loop over the buffer. And while P is the index is less than the, while we're not at the end of the buffer, we're going to set CH to P. So maybe CS is like a cursor, or maybe it's a character. Then we're going to switch on the state. And we get this comment here, HTTP methods get head post. If we're at SW start, we'll set the request start to P. And if the character is essentially a new line, then we're going to break. SW, something word. I'm not really sure what SW is yet. If the character is between these comparisons go the opposite way. Okay, so I think this is not a capital letter, and it's not an underscore, not a dash. Then it's an invalid method. Otherwise, we set state to the SW method. So I guess we were at start, and now the new state will be method. We're going to break. I kind of want to know what the state is. So let's see if we can look in the tags here. In fact, this is such a small number of files that maybe we'll just stick to Emacs. Stop that. We don't want HTTP on Nginx. Okay, so the request has, I guess, a signature, which is HTTP. It's associated with some connection. It's got, I guess, a context, a main conf, a serve conf, a loc conf. I don't know what those confs are. A handler pointer, which is a pointer to a read event handler, a pointer to a write event handler, a cache if we're using an HTTP cache, an upstream, some array of upstream states, a pool, a buffer called header in. So header input and output buffer is a request body, lingering time, start, seconds and milliseconds, a method, an HTTP version, a request line, URI, args, extend, like extension, not sure, unparsed URI, method name, HTTP protocol, schema, an out chain, a pointer to the main request. I guess if we are part of a chain, a parent, postponed, post sub request, posted requests, a phase handler, content handler access code, some variables, and some PCRE should be regular expressions and captures. These are captures for regular expressions. Limit rate and limit rate after. So this is probably like TCP rate limiting. Header size, request length, error status, HTTP connection, stream, v3 parse. Maybe this the parser changes between versions. The log handler cleanup, count, sub requests blocked, AIO, I guess asynchronous IO, HTTP state, complex URI, quoted URI, etc. Lots of stuff. Do we want, let's figure out where, well, so this like SW start stuff is, there's some gRPC module. We have a v3 parse. And this enum is going everywhere. Mail parse Nginx files. So I still don't know really when the state is set on the request, but it's set at some point. At any rate, if we're at the end of SW start, then we set SW method, and that's the next thing. And so we look at if the character is the space character, and if the next, I guess p-1, if the previous thing that we were pointing at is the method end. No, we set the method end to p-1 because I guess we're at a space, so the thing that came before us was the end of the word. We set m to be the request start, and we switch on p-m. So that should be the request. Is the difference between the start and the end, essentially. And if it's 3, it's really the distance between them, I guess. Then we check if it's a get request or a put request. Those are the 3-letter requests. Otherwise, it might be 4. We look in the second letter, and if it's O, then we're either in post, copy, move, or lock. Otherwise, it's head. And so why not look at the first letter? I guess this is it allows us to have fewer cases because so many share an O. We're kind of doing tree branching. And if we had looked at the first letter, we would have to do 1, 2, 3, 4, 5 if else blocks, whereas we only really have to do, well, it's the same amount, but I guess by looking at O, we cut down more quickly. And it doesn't look like any of these. There's not like 2 H's or 2 C's or 2 M's or anything. All right. And then what else? Case 5, MK column. I don't know what that is. And then, but also patch trace. What is MK column? Hello. Hello, Heidi. Hattie. The WebDAV MK column is some WebDAV thing, it looks like. New collection resource. Okay. I think we were in Emacs. All right, and then so these are just the different HTTP methods: delete, unlock, propatch, propose patch, maybe. Propatch. Prop patch. I missed a P. It's also WebDAV related. Something about WebDAV. Give it to the browser. So I don't get confused. All right. And then if we're done here, then we're also an invalid method, but now we check to, I guess this is like no, this is the same as before. We're checking that we're out of the defined method character space. Although it seems like what if we're not out of that space? Then we just keep going. We're going to hit break. So I'm not sure. All right. And then we are done here. So did we switch cases? So we're setting the R method kind of depending on what the name was. So for example, if we got put, we'll set the R method to Nginx HTTP put. And so that's essentially reifying the string into a type that's visible or can be seen by the compiler. So that's setting the type. Do we change the state? Yes. If we don't error out here, we change the state to SW spaces before URI. So this is presumably going to just consume spaces until we get to the URI. And we're going to look to see if we're in a slash. And if we are, we're going to go to the after slash and URI. And we're going to set C to the cha we got ORed with X20, cast as a UCAR, and check that it's between A and Z. And set our schema start to P. I guess it's the start of the schema because we're not a slash. And we're going to break. And then we're going to switch on CH. If it's a space, we break. And by default, we're going to say parse invalid request. So okay, so this is an if. And I was confused for a second about why we weren't consuming the spaces first. It seemed like we were assuming that this was a character, and really we're just getting the C as an ASCII character and then checking where it is if we're starting a word with it. And so we did two state changes. One is we're after the slashes in the URI, and one is that we're looking at the schema. And so this is just more parsing. This is a pretty interesting parser that seems to be focused on efficiency. We've seen other parsers using like parser combinators, for example, in Haskell. This one seems to be focused on parsing quickly because it's Nginx and we're trying to get requests handled at high velocity. And we've got this state machine and we're kind of moving through the state machine to determine where things are. But I'm going to move along. We have parse header line. This is presumably for parsing a header line. We have the enum here as before, but we have different states. We have start, name, space before value, etc. And the comment above the other enum said that this, I think it was saying this inline enum gets converted to a jump table by the compilers. The last null character is not needed because string is 0 terminated. Okay. So this is some lowercase thing. I don't really know what's going on. We see the ordinals 0 to 9. We see the lowercase alphabet twice. This is presumably some sort of lookup table that's going to help us do fast stuff. And this is for parsing the header line. Let's see where lowercase is used. Okay, I think these null characters are because maybe this is like the whole ASCII table, and these are just where in ASCII these things are. So lowercase, every I forget which one comes first, but one of these is the identity map between the lowercase letters in themselves, and the other is the map between the capital letters and their lowercase versions. And then we have some a thing for parsing the URIs, and we can parse a complex URI. I don't know what makes it complex. Maybe it has an embedded URI or something. And this is parsing. So let's look at some other stuff. Maybe request. So the request has headers, of course, and you've got these defined. These are, I guess, these probably come from the standard, like, although not. I guess not, because we had to parse the string to define them. So you have like post, get, the method, the methods, copy, mcall, and prop patch we saw were methods for WebDAV, and so on. And we have like a define for invalid header, and so on and so forth. We use a special code for the plain HTTP requests that are sent to HTTPS port to distinguish it from a 4XX in an error page redirection. So this is like if you send plain HTTP to a HTTPS endpoint, you get an error, and I guess Nginx is keeping track of internally of like when that happens. The header struct has a name, which is a string, an Nginx string, an offset, which is an int, and a handler, I guess, to handle the header, I assume. We have a header out, which has a name and an offset. And then what is this? This is a big struct. The headers in T. Yeah, I see some browser stuff, browser names like Conqueror, Chrome, Safari, Gecko, Opera, Microsoft Internet Explorer, and Microsoft Internet Explorer 6. But we're also keeping track of the connection type chunked. And so I guess these are just, we're putting the headers into a struct. So you see standard headers like X forwarded for accept encoding, and so on, host connection, etc. This is just a struct, a CFI'd version of the HTTP header. And then this are the output headers, I guess. We have headers, trailers, status line. So like when you make a request, you get a status back. Server, etag, cache control, like how long to keep it, and so on. And the request body has a temp file, I guess, for in case the request gets written to disk, some a chain, or rather buffers, sort of buffers for chaining or buffer stuff. I'm going to guess that the actual content is in buff, but I'm not sure. Off T, I guess offset type, the rest of the body, maybe the amount received. More stuff about request chains, some chunked stuff. I don't know whether this is keeping track of the chunks or keeping track of whether things are chunked or something along those lines. We have a handler, which is a post handler. I don't know if that's means post request, or if it's I don't know if it's meaning post in the sense of after, or if it's post in the sense of HTTP post. Whether something about needing buffering, filter, I'm not sure what filter means here, and last sent and last saved. And so on and so forth. The connection has an address conf. I don't know what conf is. Maybe I don't feel like configure makes a lot of sense, but some address conf, a conf context, SSL server name, so on and so forth. Busy and busy. I guess whether the connection is busy, whatever free is, maybe that's free elements of the chain, and maybe these are like booleans for SSL or proxy protocol. No, something for keeping track of SSL and proxy protocol. I'm really curious what conf is. Conf default server configuration for this address port. So it is configuration. So it's, I guess, looking up the Nginx configuration for this address and port. We have 44 seconds left. And I'm not sure what else we want to see. The name of the game so far is we've seen the parser. We've seen a bunch of structs that are essentially, you read the HTTP spec and you come up with corresponding structs for them, which on its own is probably not a hard exercise. I think that the Nginx people have put a lot of thought into speed and optimization. And so you probably couldn't write something as fast as the Nginx server just by reading the HTTP spec. But that's kind of the perspective of understanding HTTP that's more of a detail than something that we need to fundamentally understand. So our 30 minutes is up for this. Let's take a quick look at the HTTP, Nginx HTTP header. I don't think we're going to see anything fundamentally changing our viewpoint of what's going on, but we'll take a quick look at it. It's not so long. We have a few if-def type stuff, and we're mostly just defining like functions and types and stuff. Like Nginx, HTTP, read client, request body, and so on and so forth. Update location config. So there's a mixture of like config stuff and also handler stuff and processing headers and those sorts of things. And we have some structs here, like a status, which has which HTTP version are we? The status code, count. I'm not sure what count is, but start and end, and some chunk stuff. And that's Nginx, at least the amount that we will see in half an hour. That's all for me. Thank you for watching. And if you enjoy watching these videos, please tell your friends and your lovers and your friends' lovers